Every microwave in your kitchen runs on exactly the circuit we're building today, and you've triggered it 1,000 times without ever thinking about it. Close the door. Nothing happens yet, and it shouldn't. The microwave doesn't turn on just because the door's shut. Now, without touching the door, press start. Nothing happens either. Do both at the same time, door closed, start pressed, and now it runs. Try opening that door while it's running, and it doesn't just get inconvenient. It kills the power instantly. A microwave that could run with the door open would be cooking whatever's standing in front of it, too. That's the microwave's entire safety design in one sentence. Neither condition alone is enough. Both together, or it doesn't run at all. And that exact rule is the circuit we're building in this episode. Last episode, we built the NOT gate. One transistor, one job. Flip whatever comes in. That's the simplest decision a circuit can make, and it only ever has to look at one thing. But the microwave's door and start rule needs to look at two things at once, and only let something through when both of them agree. That's a genuinely different question, and it takes a genuinely different piece of wiring to ask it. Today we build the circuit for, is this true and is that true at the same time? Here's how you build a question like that out of nothing but switches. Take two transistors and wire them one after the other. The first one's output feeding straight into the second one's input, like two locked gates set end to end in a single hallway. Current has to get through gate 1 before it can even reach gate 2. Before I tell you what that buys you, think about it for a second. If gate 1 is locked, does it matter at all whether gate 2 is open? It doesn't. A locked hallway is a locked hallway, no matter how many gates further down happen to be wide open. The only way anything gets from one end to the other is if every single gate along the way is open at the same time. Remember what actually opens a transistor's gate from 2 episodes back. Below a certain voltage, no channel forms, and current simply can't get through that section of hallway. Full stop. Above it, a channel opens and that section clears. Nothing about that rule has changed here. Each transistor still only cares about its own input, minding its own business. So walk the whole hallway. First transistor low, blocked right at the start, and it genuinely doesn't matter what the second one's doing because you never even reach it. Second transistor low, also blocked, even if the first one's wide open, because now you get stuck one step further down. The only way current makes it all the way through is if the first input is high and the second input is high. Both, at the same instant. That's the whole idea, and it's exactly the microwave's rule, rebuilt out of 2 transistors. Neither gate alone gets you through, only both together. Every gate needs a truth table, and this one has 2 inputs, so quick guess before I show you. How many different combinations of 2 switches, each either on or off, do you think there are? 4. Off, 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 on, off, on, every possible pairing. Walk them one at a time. Both inputs low, hallway blocked right at the start, no path. First high, second low, still blocked, just one step further down. First low, second high, blocked at the very first gate this time. Doesn't even matter that the second one's open. And only when both inputs are high at once does a path exist all the way through. 3 rows of no. 1 single row of yes, the one row where both switches happen to agree. Here's a neat thing you probably weren't expecting. This exact truth table is also a multiplication table. 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, only 1 times 1 gives you 1, and behaves exactly like multiplication. Which is why, in Boolean algebra, it's actually written as a times sign, A times B. Multiply by 0 anywhere in the chain, and you kill the whole result. 1 weak input ruins everything, same as 1 locked gate ruins the whole hallway. There's one more piece hiding in the circuit that I'm deliberately not building today. Getting a clean, ready-to-reuse signal out the far end of that hallway, one strong enough to actually drive whatever gate comes next in line, takes one more small addition. And that addition is exactly why the 2 gates coming up in a couple episodes, NAND and NOR, turn out to be what real chips actually build first, with AND and OR built out of those afterward. For today, the idea that matters is the one you just watched. 2 transistors, one after another, and a path that only exists when every single one of them agrees. Every gate gets its own symbol, and AND's looks almost like a capital D, flat on the back, rounded on the front. 2 lines go in on the flat side, 1 for each input, and a single line comes out the rounded tip. Flat back because it's taking more than 1 input at once. Rounded front with no small circle at the tip because unlike the NOT gate's sharp inverting point, nothing here gets flipped. Whatever goes in stays in the same sense. It just has to agree with itself first. You've written this exact logic yourself, probably without noticing, every time you've typed the word "and" into a piece of code. Think about a bank's login screen. Password has to match, and the account can't already be locked from too many failed attempts. Get the password right, but the account's locked, denied. Account's fine, but the password's wrong, denied. Only get both right at once, and the door opens. Same hallway, same 2 locked gates, just written as a sentence instead of soldered onto a board. Or think about a sprinkler system on a golf course. Temperature has to be above freezing, and the schedule has to say it's watering time. Skip the temperature check, and you're spraying water onto ice in January, coating the whole green in a sheet that kills the grass underneath. Skip the schedule check, and you're running sprinklers in the middle of a tournament. Neither check alone protects anything. Both, together, are what keeps the actual mistake from happening. 2 transistors in series gave us a gate that needs everything to agree, all at once, or nothing gets through. Next time, we try the exact opposite arrangement. The same 2 transistors wired side by side instead of one after another, and it turns out just one of them being on is suddenly enough. That's the OR gate. And it's next.